Hello, everyone. One of my students asked about a question from one of Gene Coley's problems in Chapter 9. It was where a neutron was running into a stationary alpha particle, and then the two leave, and they give you the kinetic energy of the neutron beforehand and the kinetic energy of the neutron after the collision, and they ask you to find the two angles. When I was trying to work that out, I was trying to avoid one particular algebraic step, mainly because I was using some of the symbols, but also numbers. And it turns out that's really the best way to do it, even though it seems kind of long. So I thought I'd go ahead and make a video of that. I'm obviously changing the problem, so to make something sort of equivalent, but not the same as Gene Coley's. So I hope y'all enjoy the solution. Here it goes. Switch to my document cam. So you can see I have a 1 kilogram particle with a kinetic energy of 1,000 joules. I'm not given the initial velocity, but we can always find the velocity from the kinetic energy by multiplying the kinetic energy by 2, divided by mass, and taking the square root. It's going to run into a heavier particle, which is 4.00 kilograms. Its kinetic energy is 0, and its initial velocity, which I call V4I, is, of course, 0. It is an elastic collision, and they tell us that I'm telling you that the kinetic energy of the first particle after the 1 kilogram particle after the collision is 808 joules. I don't know what the first particle's velocity is after the collision, but again, we can figure that out. I don't know the kinetic energy or the velocity of the 4 kilogram particle after the collision. But really all I want to know is what is theta 1 and what is theta 4. Again, I can get this because the collision is elastic. I know kinetic energy before the collision, which was 1,000 joules, has to equal the kinetic energy after the collision. This is 808, so this one's going to have to be 192. So from that, I can then get the velocity. So first off, just using that fact, I'm going to say the kinetic energy of 4 is equal to 192 joules. And that means the velocity 4 is 9.80 meters per second. It turns out using the square root of 2 ke over m is equal to the velocity. It turns out that the velocity of the 1 kilogram object after the collision is 40.2 meters per second. And it turns out that the velocity of the 1 kilogram object before the collision, again using square root of 2 ke over m, is equal to 44.7 meters per second. So that all came from the definition of kinetic energy being 1/2 mv squared, and the fact that kinetic energy is conserved. And from that, we now know all the velocity magnitudes. It's just a matter of solving for these two. So what we do is we set up the conservation of momentum in the x direction. So P sub x. The initial momentum, of course, is just m1 v1. The final momentum is equal to m1 v1f. But now I need the x component, so I'm going to take the cosine. So it'll be cosine theta 1 plus m4 v4. Since I didn't have a v4 initial, I don't need to subscript that with a final. Again, that one will be cosine theta 4. And that's the conservation of kinetic energy, or excuse me, conservation of momentum in the x dimension, or in the x direction. I'm going to call that equation 1. Now, doing P sub y, conservation of momentum in the y direction, initially nothing's moving in the y direction, so the initial momentum in the y direction must in fact be 0. Initial momentum, or excuse me, the remaining momentum after the collision has this particle going off this way, so I got to take the sign of that, and that's going to be a positive y component of momentum, and this one's going to be a negative. I'll actually force that negative sign in, so I'll get m1 v1 final sine theta 1 minus, again, that's because this one's going down, m4 v4 sine theta 4, and that's going to be called equation 2. Now, the trick is, and this is what I was trying to avoid when I was trying to help my students, the trick is, it really is helpful, believe it or not, to square these two equations. So if I square this first equation, I'm going to get what I will call equation 1 prime, okay? The left-hand side becomes m1 squared v1 squared. The right-hand side becomes the square of this one plus the square of this one plus 2 times the product. That's the way you do squares of binomials. And it'll save you a little bit of time by knowing it that way. So I'm going to say m1 squared v1 final squared cosine squared theta 1 plus m4 squared v4 squared cosine squared theta 4. Now the product of the two would be plus 2m1 m4 v1 final v4 times cosine theta 1 cosine theta 4. So that's it. That's the square of the equation. I just barely fit it in the page here. Let me move my camera over a little bit so it'll help. So I just barely fit it on the page. Now you can see why I was trying to save a little paper. So that's equation 1 prime. Now I'm going to square this one, and obviously that's going to be a lot simpler. I'm going to call this equation 2 prime. Okay. So when I square the left-hand side, obviously I just get 0. When I square the right-hand side, I get the same thing. This one's going to be squared, this one's going to be squared, and then it's going to be 2 times the product. And notice that minus is going to make it a negative. So I'll get m1 squared v1 final squared sine squared theta 1 plus m4 squared v4 squared sine squared theta 4 minus 2m1 m4 v1 final v4 sine theta 1 sine theta 4. And this is the whole reason we did this. Notice this sine theta, cosine theta, cosine theta. That looks like one of our addition of angles or subtraction of angles trig identities. Plus, you notice the sine squared plus cosine squared, both of those have the same coefficients. So that makes me think, oh, I could probably add these two, and then that's going to cancel out. And that's exactly what we're going for. So what I'm going to do is I'm going to take 1 prime and add 1 prime, paper back in here, add 1 prime and 2 prime. And from that, I'm going to get m1 squared v1 squared is equal to m1 squared v1 final squared. And of course, that's going to be cosine theta 1 squared plus sine theta 1 squared, but sine squared plus cosine squared is just 1. So I'm just going to leave this as a 1. Same thing's going to happen with this one. The m4 squared v4 squared cosine squared theta 4 plus m4 squared v4 squared sine squared theta 4. That's a sine squared plus cosine squared. So I'm again going to get just a coefficient of 1 with m4 squared v4 squared. So I'll say plus m4 squared v4 squared times 1. And that's because cosine squared plus sine squared is equal to 1. Now on these two, I'm just going to make it plus 2m1 m4 v1 final v4. But now I'm going to write the positive one first, which should be cosine theta 1 cosine theta 4 minus sine theta 1 sine theta 4. Okay, I know that got kind of small there, but it's cosine theta 1, cosine theta 4, minus sine theta 1, sine theta 4. Well, that looks a lot like a trig identity that you may or may not have used before. Hopefully you've at least seen it. And that specifically is the cosine of A plus or minus B is equal to cosine A, cosine B, minus or plus, so the plus goes with the minus and the minus goes with the plus, sine A, sine B. So we can change this whole thing right here. That stuff that you couldn't read that well, but I did read out to you. That is cosine theta 1, cosine theta 4, minus sine theta 1, sine theta 4. Since it's minus, I got to use the bottom sign, which is plus. So I'm going to say this is cosine theta 1 plus theta 4. Now, that gives me an equation with one unknown, and it's not an unknown that we wanted. It's actually the sum of the two unknowns that we wanted, but that can that can be used along with another trig identity to find one of the angles, and then the other one just by realizing what the sum is. So now we can do that. So I'll plug in the numbers. This becomes m1 squared is 1.00 kilograms squared. V1 was 44.7 meters per second squared equals 1.00 times 40.2. Both of those are squared. So that takes care of that term. I've done this one. I've done this one. Now M4 is plus 4.00 squared. V4 is going to be 9.80 squared. That's a 0.80. And of course, that's times 1. Plus 2 times 1.00 times 4.00 times 40.2 times 9.80 times the cosine of theta 1 plus theta 4. So that's easy enough. I can see that theta 1 plus theta 4 is going to equal the cosine inverse, or the arc cosine, if you will, of all this junk. Now notice what I'm going to do. I'm going to do 1 m1 squared v1 squared minus m1 final squared, or m1 squared v1 final squared minus m4 squared v final, or v4 squared. That's just literally the Pythagorean theorem. It's the hypotenuse minus the two legs squared. The hypotenuse squared minus the two legs squared. So what that tells you is, in the event that that you happen to get 0 in the numerator, meaning the sums were equal to, or basically like a right triangle, then you'd automatically know this angle would be 90 degrees. So that's also an easy way to remember this final result. I'm going to go ahead and put it in. I get 1998.1 minus 1616 minus 1536.6. So notice this is the hypotenuse, basically, right there, squared, and this is one of the legs squared, and this is the other leg squared. As you can tell, if the Pythagorean theorem held, meaning theta 1 plus theta 4 is actually equal to 90 degrees, then this top would give you 0, and obviously the inverse cosine of 90 degrees is 0. Now I've got to divide this all by the 2 times 1 times 4 times 4.0, 40.2 times 9.80. Well, that turns out to be 3,151.7. You can check all the units. I've done it before. It actually works out. And that gives me, when I take the cosine of this, I end up taking the inverse cosine of, and I'll put the numbers here just so you can verify it, negative 1.155 times 10 to the negative, or excuse me, 10 to the third over 3151.7, and that gives me 111.5 degrees. So I now know what the sum of the two angles are. So that tells me what I really want, at least in the the question that the student asked me about, they really just wanted to know what theta 1 was. So if I solved this for theta 4, then when I solve the next step, the first answer I'll get will be theta 1, which is what I'm really shooting for. So I'm going to say 111.5 degrees is equal to theta 1 plus theta 4. That means theta 4 is actually equal to 111.5 minus theta 1. So now I can go back in equation 2, and that's equation 2, not 2 prime, and plug this in, and I'll get 0 is equal to, I'll go ahead and put in the numbers, what the heck, M1 V1 final, that'd be 1.00 times 40.2 times the sine of theta 1, okay, minus M4, which is 4.00 times 9.80, which is V4, times the sine of theta 4. Well, theta 4, I'm now going to replace with 111.5 minus theta 1, and you see we now have one equation and one unknown. So we can actually solve this. And in fact, it's obviously it looks a little difficult right now, but if I use the sum of the angles formula, another trig identity, then I can actually break this up into something useful. So that's what I'm going to do. What I know is that the sine of A plus or minus B, we have a minus on ours, of course, the sine of plus or minus A plus or minus B is equal to the sine A times the cosine B plus or minus cosine A sine B. So we have that trig identity. So I'm going to replace this stuff right here with sine of 111.5 cosine theta 1 plus, excuse me, we had the minus, so I got to go minus cosine 111.5 times the sine of theta 1. So that's what's going to replace all that stuff. See if I can get a better focus on that. Sometimes putting my pen down here helps. It's just the blue is not a good color to write on. All right, so now I can put all these numbers in, and what I'll ultimately get is 44.7, or I'll say 0 equals 44.7. Oh, not 44.7, excuse me, that's 40.2. 1 times 40.2 is clearly not 44.7. That would be a problem. So 40.2 times the sine of theta 1 minus, now 4 times 9.8 is 39.2. So minus 39.2 times the sine of 111.5, or excuse me, 111.5 times the cosine theta 1 minus cosine of 111.5 times the sine of theta 1. Well, as you can tell, once I distribute this 39.2 and take these sines and cosines, then I'll have two sine terms that I can combine, and then I'll have one term with a cosine, which sets us up nicely to end up getting a sine theta 1 over cosine theta 1, which is a tangent theta 1. And obviously, we could take the inverse tangent to get all that. The result becomes 0 equals 40.2 sine theta 1 minus 36.475. Just carried a buttload of sig figs there. Don't know why. Just playing with it, I guess. Cosine theta 1. And then minus 14.36 times sine theta 1. So I'll combine these two terms to get the sine theta 1. and then I can pull this over there and have a cosine theta 1, and then I can solve for sine theta over cosine theta. I end up getting 36.475 times the cosine theta 1 is equal to 40.2 minus 14.36, which is 25.84 sine theta 1. So that tells me that if I solve for sine theta over cosine theta, which is equal to tangent theta, and those are all theta 1s, of course. If I solve for that, then I really have to take the inverse tangent of 36.475 over 25.84. Take the inverse tangent of that, and I get theta equals tangent inverse of that, and that gives me 54.69 degrees. Y'all can check that yourself just to make sure, but I'm literally just taking the inverse tangent of that quantity. I think I didn't write down what that quantity was, but it is pretty trivial. Now that you know theta 1, or excuse me, now that you know theta 1, so theta 1 is equal to 50, let's call it 54.7. Then theta 4 is equal to 111.5 minus 54.7, which should give us 56.8. You can check that. That's 100. That's 110. And then that's 111.5. So yeah, that's right. So my final answers are theta 1 equals 54.7 and theta 4 equals 56.8. But that's a nice trick to make use of by squaring the p or the x component of momentum and the y component of momentum equations. You end up getting a sine squared theta squared, or sine squared plus cosine squared that just reduces to 1, and you get another one, and then you end up getting just a trig identity for the sum of two angles, and that allows you to solve for the rest. So I hope that will help you, and that actually should work anytime you have a particle bombarding a stationary particle, whether they're the same mass or not. You'll end up getting this exact same expression. And in fact, if they're the same mass, then you'll see what happens. You end up getting all the masses cancel out, and you'll get theta equals theta 1 plus theta 4 equals 90 degrees, which is a fundamental idea in elastic collisions. I hope that helps. Have a good day.